We're going to look at disaccharides now, which are two monosaccharides joined together. And we're going to see that they are joined together by something called a glycosidic linkage. Here's an example of a disaccharide. This disaccharide is called maltose, and maltose is two glucoses that have been joined together with a glycosidic linkage. A glycosidic linkage is basically an ether functional group. How can you make an ether? You can take two alcohols and condense them together. Remember that condensation is a joining of two molecules by the removal of water. So if I take these two sugars, you can see there's an alcohol group here and an alcohol group here. I can remove water and then that forms an ether linkage here. And it's drawn like this, or sometimes with a straight line there. There's no carbon here. That's just a stylized showing of the glycosidic linkage. Because this was alpha here, this is called an alpha 1, because that's the number 1 carbon. And then that's 1, 2, 3, 4. So this is called an alpha, because it's down, 1, 4 linkage. So alpha, because it's down, 1, 4 linkage. And so this is how it is described right here. This is an intermediate. Maltose is an intermediate in the hydrolysis of starch, because starch is basically made up of glucose molecules that have been attached to each other. Here is lactose. This is the sugar that you find in milk. What is lactose made of? It's made of galactose combined with glucose. Here you see this is a beta galactose. There is a beta glucose. What we're going to do is form the glycosidic linkage here. And what you get is beta, and remember this is 1, and this is 1, 2, 3, 4. So this is a beta 1,4 linkage. Sucrose is glucose that has been joined to fructose. So the table sugar, sucrose, is half glucose, half fructose. To make the linkage, it's going to be alpha 1, and then it's going to be joined to a number 2 carbon over here. So this carbon right here is joined to this carbon here through the glycosidic linkage. So this is alpha 1, and then this would be 2. And this oxygen is up, so that's beta 2. So this is alpha 1, beta 2 glycosidic linkage. And that's what we have in sucrose. Polysaccharides are many sugar units stuck together. So in a polysaccharide, you have hundreds and hundreds and thousands of sugar units attached together by glycosidic linkages. Because they are so large, they're not water soluble, they're either water suspendable or they will form colloids. But this is not going to be soluble like sugar is in water. The polysaccharides are starch, glycogen, and cellulose. All of these are glucose polymers. The only difference between them is the type of bonds that they have. Amylose is a starch, and it's all glucose molecules, alpha glucose molecules, attached by alpha 1,4 linkages. So you have 1,4, 1,4, 1,4, and you just have thousands and thousands of these glucose molecules. Amylose is one of the simplest starches, and it's the kind of starch you would find in saltine crackers, some in breads and rice and things like that. Then you have something called amylopectin, and amylopectin is just like amylose, except instead of being one long chain of glucose molecules, it's a bunch of branched chains. So instead of just being a big long chain, you have several branches on it. The branches all are going to be just like the amylose. It's just when the chain connects to the chain in the branch, instead of being an alpha 1,4 linkage, it's now an alpha 1,6 linkage. So here's alpha 1,4, alpha 1,4, alpha 1,4 in the long chain, alpha 1,4, alpha 1,4 in the long chain. But where it connects to make the branch, you get alpha, see it's down, 1, 6. This is the number 6 carbon. 1, 2, 3, 4, 5, 6. So an alpha 1,6 linkage. In amylopectin, there are long branches and very few of them, so it's kind of like a big long rope with a few ropes attached to it. Glycogen is something called animal starch, and this is the starch that is stored in your liver. It is just like amylopectin, but the lengths of the branches and the numbers of branches are different. It's still alpha 1,4 linkage in the main chains and the alpha 1,6 connecting the branches, but instead of having few branches, it has many, many, many branches, and they're really short instead of being long. So here's amylopectin, and this is what glycogen looks like. It looks like a hairy worm, whereas amylopectin looks like a bunch of strings all tied together. This is plant starch, this is animal starch. And then you have amylose, which is one big long chain. Cellulose is one big long chain also, but instead of being an alpha 1,4 linkage, it's a beta 1,4 linkage. Cellulose is what we consider to be fiber in food. Our bodies have no enzymes to digest them, so they pass through us undigested, and we call them fiber, and it basically gives the bulk to food moving through your intestines, which is really important to have that bulk so that things move through properly. But we can't break down the cellulose and use the sugar within it. There are some animals that have bacteria in their guts that will break down the cellulose into sugar for them to use. Cows and goats are what are called ruminators, and they contain bacteria in their stomachs that allow them to break down cellulose into glucose. The beta linkage enzymes are not made by mammals, but they are made by bacteria that are found both in cow guts and in termite guts. So cellulose is also glucose. So cotton is cellulose, and so cotton is basically glucose. And if you could eat cotton, if you could eat cellulose and get the sugar out of it, you could eat cotton or paper and be able to get nutrition from it like a termite can or even cows can. There are other sugars that we're going to learn about eventually. Glucosamine is an aminated glucose, and there's other types of sugars that we're going to learn about. If we can go through now these questions to help you see if you've learned the material. Okay, so describe the molecule shown here. If you look, it is a monosaccharide, so 1 holds true. 1, 2, 3, 4, 5, it's a pentose. That's an aldehyde group, so it's an aldose, so all of these is the correct answer. How many stereoisomers are possible for an aldotetrose class of carbohydrates? Well, it's got 4 carbons. Of course, the aldehyde part cannot be chiral, and the bottom carbon is not chiral, so there's only 2 chiral carbons in there. 2 chiral carbons will give you 4 possible stereoisomers. All carbohydrates have the general formula CnH2nON. Well, this is false because it's only monosaccharides that have this formula. The polysaccharides lose water, and so they don't have this general formula. Which of the following statements is true about this carbohydrate? Carbon 4 is not a secondary alcohol, it's a primary alcohol. The absolute configuration of this carbon right here, the hydrogen's coming out, that's 1, 2, 3, actually 1, 2, 3. So that is R, but the hydrogen's coming out, so it's S. So this is incorrect. For number 3, the number 1 group would be this, and then this, and then that. That is clockwise, but the hydrogen's coming out, so it's counterclockwise, so 3 is correct. The molecule is chiral. It is not achiral. This group is not the same as that, so it can't be meso. Which of the following disaccharides is also known as table sugar? Well, that's going to be sucrose. Which of the following is a D-ketohexose? Well, this is D, that's L, that's D, that's L. And you're just looking to see which side the hydroxyl group is on. This is a ketone, that's a ketone, and that's a ketone. If we look now, and this is an aldehyde. So this is D, this structure represents the beta anomer of D-galactose. Well, right here, let's look at this carbon right here. That's the anomer, the anomeric carbon. This is up, so that would be beta. So that is true. Which of these would lead to the cyclic pyranose? Pyranoses are going to be 6-membered rings. So let's look at this. This is going to be, this is down, that's down, that's down. So down, down, down would mean right, right, right. So if I look at this, it would have to be this one right here because everything's on the right. How can you best describe this sugar? A furanose is a 5-membered ring and a pyranose is a 6-membered ring. There's a 5-membered ring here. Okay, if I look at this, it's going to be D. We're not worried about that. But then we look at the anomeric carbon and we see that's down. So it's an alpha, and then it must be a furanose. So it's either this or this. This one's right too. Which term best describes the disaccharide here? Well, let's look at the linkage. This is alpha down, 1. Let's see where it attaches. 1, 2, 3. So this is an alpha 1,3 linkage. So it's going to be 1.